Hello friends, welcome to this video on set theory. This video is going to speak about the relation which can be represented as graphs. So we will see what is meant by graphs in this video, how to represent relation in this video as graphs, and also we will see something special called as Hasse diagram, which represents the partial ordering relation and representing them as graph. So come on, we will move into the video. First, we will see what is meant by graph. Let R be a relation that can be defined on a set A. To represent R graphically, what we do is each element of A is represented by a point. This point is called by the name node or vertices. Whenever the element A is related to B, an arc is drawn from the point A to the point B. The arc is also called by the name edges. The arcs start from the first element of the related pair and go to the second element, that is from A to B. The direction of movement is indicated by an arrow. The resulting diagram is called as a directed graph, or in short form digraph of the relation R. If there is an edge from the point A to the point A itself, that is we have the ordered pair A, A, the arc is now called by a special name so that it starts from the vertex and gets back to the same vertex, and the name given for it will be referred as loop. So we will see how to represent relation using graphs. Example 1. Let us have A to be the set 2, 3, 4 and 6. So what we need to do first is the elements of A are represented by points. So we keep points so that we have 2, 3, 4, 6 to be represented by points. Next, what do we do is we define the relation R. How is the relation R defined? A is related to B if A divides B. So we have the relation defined on the set A, and hence I need the set R that satisfies the relation A divides B. What will be the collection of the ordered pairs that satisfies A divides B? So I know that 2 divides 2 itself, 2 doesn't divide 3, so 2 divides 4, 2 divides 6, so 2, 2, 2, 4, 2, 6 enter the relation. Next 3 divides itself, so 3 divides 3, 3 doesn't divide 2, so that is not in the picture, 3 doesn't divide 4, but 3 divides 6. So 3, 3 and 3, 6 enter the set. Next 4 doesn't divide 2, 4 doesn't divide 3, but 4 divides 4, so 4, 4 comes in the picture. And 4 doesn't divide 6. 6 doesn't divide 2, 3 and 4, but 6 divides 6 itself. So 6, 6 enters the picture. Now what we know over here is after plotting the point, we draw an arc from the point A to the point B if they are connected by a relation, if A is related to B. So what we do is if 2 is related to 2 itself, so what do we do is from 2 we start and we end an arc in 2 itself. This kind of arc which starts with an vertex and ends in the same vertex is referred by the name loop. So this arc is a loop. Next, I draw an edge from 2 to 4. So from here, I have something over here and I draw an arc, so 2 to 4. The arrow is placed in such a way that it starts from the point to the first element and it reaches the second element. So the direction of flow is from 2 to 4. Next, we have 2 to 6. So I have 2 to 6. So I draw a arrow or arc in this way. Next is 3 to 3. So 3 to 3 itself is going to be a loop. Next I have 3 to 6. So this is going to be the arc from 3 to 6. Next I have 4 to 4. Yes, I have a loop in 4 to 4. And then I have a loop from 6 to 6. This pictorial representation of the relation A divides B defined on the set A of 2, 3, 4, 6 is called as the digraph representing the relation R. What is the necessity for digraphs? Normally, when we are planning to do a network, a source resource allocation or travel allocation or source allocation of that kind, then we need to mark paths which will be able to help us define how we can maximize the profit and minimize the losses. So we keep sure that we will avoid majority of the crisscrossings of these lines. So a common rule that is going to be followed to avoid more of these crisscrossings is that the lowest or the least elements are placed in the lower deck so that we can avoid crossing them again and again. And then we place the bigger numbers in the upper deck so that they will be reached or they can be moved from the lower point to the upper point. And we also make sure that relatively prime numbers, that is relatively prime means they have no common divisor among them apart from 1. So these don't have any relation among them, and hence what can be done is, if they don't share a relation, they can be placed along the same line. In which case what happens over here is 2 and 3 are relatively prime. They don't have any numbers which is going to commonly divide them. So I place 2 and 3 in the lower portion. Next comes the number 4. Keep in mind, my idea is to avoid crossing overs. So if I want to avoid crossovers, what I will have to do is, I will wisely place my number 4 to the side of 2 because 4 is in no way related to 3 in divisibility. So when I place 4 over here, I'll have to travel from all the way from over here to the opposite side to reach 4. But in case I am going to place my 4 closer to or on the side of 2, then it will be easy for me to access it. And the next thing is that the element 6. And this 6 is going to be something which is common to 2 as well as 3. So let me place it in a position where it is common to both 2 and 3. So if I am going to number it in such an order, considering the lower numbers at the bottom and the bigger numbers at the top, and placing relatively prime numbers in the same deck and related numbers on the same side, then we can avoid a lot of crossovers so that our network will become or be representing a clear picture. So I now have 2 to 2, I have a 3 to 3 as a loop, I have a 6 to 6 as a loop, I have 4 to 4 as a loop, and now I have connected from 2 to 4 because 2 divides 4, and now I have a 2 that divides 6, and now I have a 3 that divides 6. Now see, we have not made any crossovers and the network looks neat and simple. So this is how we define a digraph or draw a digraph. Keeping these basic things in mind, we move on to the next level called as Hasse diagram. This is particularly meant for partial ordering. The simplified form of a digraph of a partial ordering on a finite set that contains sufficient information about the partial ordering is called as a Hasse diagram. We quickly recollect what is meant by partial ordering. A relation that is going to be reflexive, anti-symmetry, and which is going to be transitive is referred as a partial ordering. So it has to be reflexive, it has to be anti-symmetric, and it has to be transitive. So this kind of simplified version of digraph was devised by the 20th century mathematician called as Helmut Hayes or Hasse. Like however we want, we can pronounce it Hasse or Hayes. Okay, and so what he gave was three different methods to achieve it. Since the partial ordering is going to be a reflexive relation, we know that it is reflexive, its loop has the reflexivity to be representing it, because I know that what do you mean by reflexive relation? Any ordered pair of the format A comma A has to belong to the relation. When A comma A belongs to the relation, then what happens over here? You form a loop. So loop is already a part of the partial ordering. So we need not have to show the loops when they are going to be present. The second thing which we have is going to be transitivity. Since the partial order is already transitive, we need not show the edges that may represent due to transitivity. Like we know that 2 divides 4 and 4 divides 8. So already we have a point from 2 to 4, and we also have a point from 2 to 8. So one more line that moves from 2 to 8 seems unnecessary. Already there is going to be a direction that is going to go from 2 to 8 through the point called as 4. So it says that the edges that is formed due to transitivity can be removed. We assume that all the edges are directed upward, so we need not show the direction of the edge. As I said, we place the lower numbers at the bottom and the bigger numbers on the top. So when it is completely drawn, the flow is from bottom to the top, and in which case the requisition of arrows can be ignored. So the flow is always from bottom to top. So we quickly recap the 3 points of Hayes diagram. Condition number 1, from the digraph, the base is going to be always the digraph. Okay, so from your digraph, what you do is you remove loop. Next thing, you remove edges due to transitivity. Next thing, you remove arrow so that the initial vertex is below the final vertex. Keep these 3 points in mind, so you will be getting your Hayes diagram from your directed graph. So we will apply it to a problem. Let us construct a Hayes diagram for the partial ordering A comma B such that A is less than or equal to B on the set 1, 2, 3, 4 starting from its digraph. As already said, we will follow the rules that 1 is going to be relatively prime to all the numbers and it is of smallest of all. So let me place it at the bottom. Next, I can place a 2 and 3 in the same deck because they are relatively prime to one another. And next comes 4. Will be better to place 4 over here to the side of your 2 rather than the side of 3 because it is going to be so. Now this is how we planned for, like when it was the case of division. But now what is the relation that has to be given to us is going to be A is less than or equal to B. Less than. So what will be the better way of positioning these elements? I know that 1 is less than all the numbers, and next comes 2 which is lesser than that of the remaining numbers, and next comes 3 and last comes 4. So instead of placing it in this order, when we choose it for the problem of divisibility, now we choose this order so that it will better represent the relation called as less than. Let us draw the diagram. Now I know that what is the relation? 1 comma 1 because 1 is less than 1, 1 is less than 2, 1 is less than 3 and 1 is less than 4. Next, I know that 2 is not going to be less than 1 but 2 is less than 2, 2 is less than 3 and 2 is less than 4. Next, I know that 3 is going to be less than or equal to 3 and 3 is going to be less than or equal to 4. And I know that 4 is going to be less than or equal to 4. Equality is here, so we include the points 1, 1, 2, 2, 3, 3, 4, 4 also. So I draw the loop for 1, 1, 2, 2, 3, 3, 4, 4. 1 related to 2, next 1 related to 3 and 1 related to 4. Next I have the next line 2 related to 3 and I have 2 related to 4. Next I have 3 which is going to be related to 4. So this is going to be my diagram which minimizes my crossing over. So we will try to form the Hasse diagram from over here. So what is going to be the Hasse diagram? Remove your loops. So follow your instructions. Step 1, remove loops. Step 2, remove lines of transitivity. And third one, remove the arrows so that the flow is from bottom to top. So first stage, what we do is we remove the loops. So from over here, I am removing my loops. 1 to 1, 2 to 2 and the one from 3 to 3. So this is gone. Okay. So now the step 1, remove loops is over. What is going to be the next one which we have? Remove lines of transitivity. I know that 1 is going to be less than 2 and I know that 2 is going to be less than 3. So 1 is less than 3 is going to be my line of transitivity. So what do? I remove the line 1 to 3. So the line from 1 to 3 is being removed. Okay. And again, what do we know? I know that 1 is less than 3, 3 is less than 4 and so 1 is less than 4. So this is going to be a line of transitivity. So what do I do over here? I remove the transitivity from 1 to 4. So this line from 1 to 4 goes off. Is it clear? Okay, next. I know that 2 is less than 3 and 3 is less than 4. So 2 is less than 4 is a line of transitivity. So I can remove this line of transitivity. So what do? I remove the line from 2 to 4. So I have removed all the lines of transitivity over here from this set. So I have been left out with this resultant graph. So I have removed loops, I have removed transitivity. The last thing is that I need to remove arrows so that the flow is from bottom to top. Hence, my final Hasse diagram will be 1, 2, 3, 4 with a line from 1 to 2, a line from 2 to 3 and an arc from 3 to 4. So this is my final Hasse diagram that represents the relation less than or equal to relation. Okay, so we will complete it with one more problem. Like let x be the set 2, 3, 12, 24, 36 and the relation less than or equal to be such that x less than equal to y if x divides y. Draw the Hasse diagram for x less than or equal to. We need to be very careful over here. It is just a relation R that is going to represent, but it is not acting as a less than or equal to operator. But how is the operator defined? It is defined as x divides y. Okay, so what does x less than or equal to y represent? X divides y. So if x divides y, then what are going to be the ordered pairs for me? 2 divides 2, 2 divides 6, 2 12, 2 24, 2 36. Next I have 3 to divide 6, 3 will divide 12, 3 will divide 24 and 3 will divide 36. Also 3 divides 3. Next I have 6 divides 6, 6 divides 12, 6 divides 24 and 6 divides 36. Next we have 12 to divide 12 itself, 12 to divide 24 and 12 divides 36. The next I have is 24 divides 24, but 24 does not divide 36. And next comes 36 divides 36 itself. So this is my relation. From the relation, step 1, remove all your loops. Step 2, remove the lines of transitivity. And step 3, make sure that the flow is from bottom to top so that your arrows are removed. When I am going to draw the diagram, let me place the relatively low prime elements on a same deck. 2 and 3, let me keep it here. 6 is going to be common to 2 and 3, so let me place it here. And next comes 12 and 24. 24 is going to be divisible by 12, so I can place 12 over here. 24 and 36 have no relationship among them, so let me place 24 over here and 36 over here. So the flow will be 2 divides 6, 3 divides 6, 6 divides 12, 12 divides 24, and 12 divides 36. So this will be the final Hasse diagram if I am going to consider all the 3 conditions that has been formed for. Last one more. Draw the Hasse diagram representing the partial ordering A comma B such that A is subset of B on the power set P of S, where S is going to be the set A comma B comma C. What is meant by power set? The collection of all possible sets, like a empty set, a singleton set with A, B and C, a doubleton set like AB, BC and CA, and elements taken all at a time A, B, C. So this is going to be my power set, and I know that the power set will contain 2 to the power of n elements, like 2 to the power of 3, so it has to have 8 elements since we have 3 elements over here. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 elements. I know that empty set is a subset of all these sets. A is going to be a subset of AB and AC. Similarly, B is a subset of BC and AB. C is a subset of BC and CA. And A is also a subset of ABC. So it is a subset of AB as well as it is a subset of ABC. It's like a transitivity. A subset of AB, which is a subset of ABC. So from here to here, this is going to be transitivity. This has to be removed, and so on. So the relation which is being followed here is subset. So how to comprise this as an Hasse diagram? The least of all, what do we do is we place the null set at the bottom. So null set, the empty set is placed bottom. Next, elements one at a time. A, let me take B, and let me take C. And next comes your A comma B, which is going to be there in the center, and next with B comma C, and the last one with your A comma C and B comma C. And on top of all it is the tripleton set. This is my A, B, C. So now if I am going to connect, null set is a subset of all the sets. So it will be starting from null set to the singleton set. And my set A is a subset of AC. My A is a subset of AB. My B is a subset of BC. My B is a subset of AB. My C is a subset of BC, and my C is a subset of AC. And last, this AB, AC, BC are all subsets of the tripleton sets ABC. So this diagram which we have finally is going to be our Hasse diagram that represents the relation subset of defined on the power set P of S of ABC. I hope this concept on digraph and Hasse diagram, which represents the partial ordering, is now clear for you people with the examples defined. Happy learning, continue learning. Thank you.